Hello everyone. So today we are going to see the second video in the Scikit-learn library, and we're going to talk about the linear modeling. So we will see the prerequisites, then we'll see what linear regression and what logistic regression is. So let us see the prerequisites first. So like we discussed in the previous video, Python is a prerequisite for this whole module or for this whole library because it is in Python. And for this, additionally, you should know about the linear regression model and also the logistic regression. And good to know is pandas, numpy, scipy, matplotlib, because you use those to do some basic operations, maybe on arrays or data frames if it is about pandas, and it would be really good if you already know that. So let us see what linear models in scikit-learn are. So there is linear regression. There's a lot of other linear models in the library, and you can definitely explore them, but we are going to talk about the few ones which are widely used. So now linear regression again has two parts. One is simple linear regression, the other one is multiple linear regression. So it is one of the best statistical models that studies a relationship between two variables, one being a dependent variable and not two actually, two or more than two, and another being a set of independent variables. So if you just take two variables and that will be your simple linear regression, but if there is a set of independent variables, that would be the multiple linear regression. So let us see how simple linear regression looks like. So if you see the graph over here, so there are a lot of blue dots, or these points as you call it. So these are nothing but the data that you have. For example, your data will have some x value and some y value. So just plotting them over here is giving you these blue points. And what linear regression does is it tries to generate a line that is best suitable for the model. That is, it will create shortest distance for each point. So it has to try to create the minimum possible distance between each point. So over here, this red line is showing us the best model, the best linear regression, and it has an equation basically. So you can see the equation is y equals to bx plus a, where b is the slope and a is the intercept. Now how do you calculate the slope? So slope is again calculated by r into sx divided by sy, where r is the correlation between x and y, sx is standard deviation of x, and sy is standard deviation of y. So again, these standard deviation also has its formula, and you need to know that. So that was about what simple linear regression is. You should already be knowing this, but just to jog your memory, I talked about it. Now let's see a sample code. Yes, so let's see the code. Before seeing the code, actually, let us see what the official documentation of scikit-learn contains for linear models. So if you see, you can just see the link. You can open scikit-learn.org, and you'll find a lot of things over there. So you can go into detail, or just look at it as an overview, or just a specific thing that you want. So in linear models, it has so many options. If you see on this left hand side, so you have ordinary least squares, you have elastic net, there's Bayesian regression, logistic regression, perceptron, so polynomial regression. There's a lot of things. You can definitely go through them and explore what kind of models are more suitable for you. We will just talk about the more popular ones, like I said. And this is the code from last time, where we just imported a data set from the scikit-learn library and just saw the column names and the few rows of it. So now let us start coding for linear regression. So let us begin then. I'll just write a text over here signifying that this is linear regression, and let's start with the code. So we'll require pandas library since we are going to use a data frame, and pandas library is used for that basically. And we'll also import data sets from scikit-learn library. We'll be using the iris dataset which we have seen before over here in the previous video. So from sklearn.datasets we'll import load underscore iris, and now we have imported the dataset. Now we have to load it into a variable. So we have used the variable iris before, we can continue with that, and iris equals to load underscore iris just like before. And now we are going to convert it into data frame. So I'll talk about why we require a data frame over here later on. It's in short, it's required for the linear regression inbuilt function which we will be using. So to convert it into a data frame, we'll be doing df equals to pd dot data frame. So over here I've used df which is just a short form for data frame. You can use any other variable, and we'll use data equals to iris dot data. So we have stored our data set into the variable iris. That's why for the data frame, the data in the data frame that we have is going to be taken out of iris where we have loaded the data set, and the columns will be defined as iris dot feature underscore names. So we have seen this before over here. If you remember, in the previous video we have seen the column names and we've stored it in a variable called call underscore names. So we used iris.feature names over there as well. Similarly over here for the data frame, what are the column headings? So the columns basically. So columns is nothing but iris.feature names. So let us try running this. So while it's running, we can move ahead with the code. And since we are going to do exploratory data analysis right now, EDA, this is nothing but exploratory data analysis. So we'll use tf.head just to see the few lines, the initial lines of the code. And yeah, you can see the small green tick over here which indicates that there is nothing wrong with the code and everything has been imported and loaded as per our requirement. So let us proceed with the code. We can check the shape of our data frame, then we can just plot it. We can do a scatter plot, df.plot.scatter, and we can take what rows can we take? Now let's see. Okay, we'll decide about the scatter plot later. Okay, for instance, let us just take petal width, and we can take petal length maybe. So if I put x equals to, I'll just copy this and y equals to, let's say, petal length. So now this completely depends. If in your data set you have some other column that you want to predict, you can put that as y, and you can take the x based on the correlation. We'll talk about it later. For now, just let's just look at the scatter plot, and let's give a title. So we can give the title as, let's just say, scatter plot. Now yeah, so I was talking about correlations, so you can also see the correlations between each and every variable. So this is an inbuilt method. It will give us a correlation matrix, and you can also see what each and every, okay, describe. So this will tell us about the mean, median, and basically it will describe each and every feature. So let us see if we have any errors so far. All good. So over here we are first printing the correlation matrix, and right, so you can see that these numbers are the correlations. Now if you see sepal length has a correlation of 1 with sepal length, so that is obvious. I mean, they both are the same thing. Now what is correlation? You should already be knowing it, but if you don't, correlation basically shows us the relationship between two variables or two features, and a correlation of 1 means a perfectly positive relationship. That means that with the increase of one value, the other value will also increase, and correlation of -1 means a perfectly negative relationship. That means increase of one value will lead to a decrease, so in the same ratio actually. So this is how through correlation you can know which one can be used if you just want to use one variable, since we are doing simple linear regression. So over here if you see this seems pretty healthy to me, like 0.96 is the correlation between petal width and petal length. So you can definitely, let's say, predict petal length using petal width, and it will be really easy for the model also. And the other correlations are not so satisfactory. Let's say over here is minus 0.1, so it is next to nothing, so there's not much of a correlation over there. Petal length and sepal length is there, but this is the best one. So we are going to try to predict, let's say, petal length using the petal width, and this is the correlation matrix. It has gone to the next line. So over here we have described. So if you see, I had done df.describe. So I talked about mean, median, mode and all. So what it shows is it shows us count, mean, standard deviation, the minimum value and maximum value, and so on. So the scatter plot. So this is the scatter plot that shows uh, petal width versus petal length. So petal width being on x column, x axis I mean. So let us proceed with the code. Now we'll do pre-processing. So let's say y equals to, we need petal width, and it is, yeah, you have to write the name of the columns as it is, and yes, restart, reshape. So you have to reshape these columns because the input that linear regression requires, so that has to be, that cannot be a single 1D array, and we have to reshape it. So that yeah, so similarly for x also we have to do. So for x we have petal length, right. So like I said, Scikit-learn's linear regression model, it expects a 2D input, and if you see that this column is really a 1D array or a one-dimensional array where you just have a single set of values, but the linear regression models expects us to give a 2D input, and that's why we have to reshape it to uh, you know present it as a 2D array. Now we have to split the data set into training and testing. So let us start from sklearn dot model underscore selection. We'll be importing the train test split. Import train test split. There we go. Now we have to declare the variables, and then we're going to split x underscore train, x underscore test, y underscore train, y underscore test equals to train test split x comma y test underscore size equals to 0.2. So over here what we are doing is we have taken since we have two variables, one is x, one is y, and we are going to split each one into training and testing data set. So basically x train will contain the training values for x variable. Similarly y train will contain the training values for y variable, and x test and y test are the data which we'll use for testing our model. And over here the size we are taking, test size, is 0.2, which means that 80% of the data is going to be for training and 20% is going to be for testing. So based on that we can evaluate a model based on various metrics. Now we will just print these, print x underscore train and print y underscore train. So let us see what it shows us. Okay, it's underscore over here. So like you can see this a lot of rows in our data set, and that's why you can see that the training data is huge and so is the testing data. So this is what we are going to do in the pre-processing. Now we can go ahead and train our model. So now we will be training the model. Let's say train model, and usually there's a lot more in pre-processing, and that's a part of machine learning and how to deal with data sets. But since this is a inbuilt data set for the library and it probably doesn't have any missing values, so we do not have to get into all of that, and we can just see how the library provides us with the directly the inbuilt code for the linear regression model. So now we'll train the model, and for training again we have to import from Sklearn dot linear model, import linear regression. So yes, now we'll put it into a variable regressor equals to linear regression. So let us check. Alright, no hurry so far. Now we're going to fit the data set into this model. Now we've just called the inbuilt method of linear regression so far. Now we will fit it. So regressor dot fit x underscore train and y underscore train. So we had split the data into training and testing data. Now we are using the training data to train the model, so that's what we split it for, and that's what we'll be doing. Now we'll print the intercept. So if you remember in the formula we had seen that y equals to bx plus c, or uh, the variables might be different, but we had an intercept and slope, so you can directly get the intercept from regressor dot intercept, and yes, and we can also print the regressor coefficient, so that is nothing but your slope. So works fine, and you can see that this is the intercept and this is the regressor coefficient. Now we can also form our own equation using this, because that's all we needed to form the equation to make any prediction. Now that our model is trained, we can try making the prediction. So we will, let's see, write predictions, and okay, so let's say score equals to regressor dot predict. And so like I said, that it expects you to give a 2D array, so we need double brackets, and we can just put any value if you want to see the prediction for, let's say, for something like we can take, let's say, 7.5. so if we take 7.5, let's see what it will predict for us. Now we'll just run this. So if the petal width, so what are we taking again? We are taking the petal width and trying to predict the petal length. So if the petal width is 7.5, the length should be 2.7 based on our model, and this is directly the inbuilt functionality, but we can also try putting these values into our equation, and maybe write the equation by ourselves. So if you want to define a function, so let's say calculate will take slope as the input, intercept, and let's say value. So now you will directly return slope into value plus intercept. So this is our function where it's nothing but y equals to bx plus c, where c was our intercept and b was the slope, and x is the value that we are using to predict. So this shouldn't have any issue. Now using this, we can just again, let's say score equals to our function name, and we'll pass the coefficient, which is nothing but the slope like I mentioned. Then we'll pass the intercept, and we have to pass a value. So we used 7.5 to predict, we'll also use 7.5 here, so we can just match it with our answer from the model, and then you can print score. So you can see that it exactly matches to the answer given out directly from the model. So now if you see that what we did was using some inbuilt methods, we directly calculated the slope and the intercept, and we built our own equation that is nothing but slope into a value plus the intercept. So the value was anything that we wanted to use to predict the y value. So it returned the same thing, so that ensures that the model is working fine. Okay, so we have calculated that, and now we can just use our test data set. So we haven't used it yet. So y underscore predictions or y underscore pred equals to regressor dot predict, and we'll use x underscore test to predict. So we are basically storing our predictions for the test data into this variable, and we can print it. So we can print it as a data frame with actual and predicted value. Since we have the data already and it has mapped values of x and y over here, where x is the petal width and y is the length, and we already know what each and every value is and there are no missing values, still we are using 20% of the data for testing. That means that we already have both x and y, but we are only going to use x and see what our model is giving as an output for y, and then we can see and compare it with the actual values. So that's what we'll try to do over here. So df underscore prediction we can take, and we can just use pd.data frame, and now we will need, so let's say actual, so we can see what the actual value is. So y underscore test dot squeeze, and predicted, so underscore red. Yes, so that seems right, and we'll just print okay. This is typo over here, right? So if you see that uh, this is an actual value of y and this is a predicted value that our model predicted, so there is hardly some difference. In this you can see this is just 0.02, in this it's 0.01, over here it's 0.18 around, and you can see how close it is to the actual value. So just imagine when you do not actually have the data with you, but if you train your model well, if you use the data properly, you do pre-processing, you can basically just predict the value that will be there, or that is missing, or that you want to see. So this is really helpful, and like I said, it is a very simple model, but it's very useful. Now we can also evaluate our model. So there are various ways in which you can evaluate a regression model. There is a mean absolute error, then there is mean squared error, then there is RMSE, that is root mean square error. So let's say evaluating the model. So again, for evaluation also we have a lot of inbuilt things in our Sklearn library. So from Sklearn dot metrics import mean absolute error. We also want mean squared error. Now these also have their own formulas, and if you want you can also calculate it without the library, but that will just basically be more lengthy, and it is very simple with the library. So we also need numpy, and so mean absolute error we can just write MAE equals to mean absolute error, and what we are using is the y test and the y predicted. So we basically want to see what is the difference in between the test and the predicted values, the actual values and the predicted values. Now similarly we can take MSE. So I'll just paste it over here, and MSE equals to mean, so we just have to change this to squared y predict. So is there y predict? Yes, there is. Now we have to see RMSE. RMSE equals to, so RMSE is nothing but the square root of MSE. So we are using numpy to calculate the square root, np.sqrt and MSE. Now you can just print, let's say MAE, print MSE, and print RMSE to see how the model is. Okay, ypredict. Okay. So we have stored it in the variable ypred, not ypredict. So I think this should do it. Right. So if you see our mean absolute error is 0.18, mean square error is 0.05, and root mean square error is 0.2. So what it basically tells us is that the error in the actual and the predicted value is just around 0.1, which is basically negligible. So it tells that the model is working fine and our model is very good. So that is mainly also because that the data was clean and we did not have to do much pre-processing. So now to train the model, we just required these 3 lines. So it is very easy when you use the library. And for making prediction, we just required this 1 line. So in 4 lines, you can just train your model and even make a prediction using the Scikit-learn library. Now, if you want to do that without using the library, it will be a long process because you have to calculate each and everything, and also calculate over here again we took the regressor, intercept and coefficient directly, but you'll have to calculate the slope and the intercept manually. So that will take a lot of more coding and lot of more time actually. So scikit-learn just brings it to you at hand in just 4 lines. You technically just require these 4 lines, but we have done a lot more things, like we have seen the correlation matrix, the scatter plot, and we have also evaluated it. That is nothing but the metrics that we're using. So there are a lot of things we did, and scikit-learn is really helpful in reducing the amount it takes for doing all these things. So that was about linear regression. So that's it from this video, and we can see about multiple linear regression, which also comes under linear modeling, and we'll see about it in the upcoming video. Thank you for watching.